Today we're going to look at the wonderful topic of rotational kinetic energy, and we'll start out as always by looking at regular kinetic energy, which is 1/2 mv squared. You might be able to guess what rotational kinetic energy is, and we'll just call it k rot for rotational. We still have a factor of 1/2. This ugly m here becomes our moment of inertia, and v squared becomes omega squared. That's all there is to it. Rotational kinetic energy is conserved along with all the other types of energies. So it's not its own separate thing like rotational momentum was. It still follows conservation of energy laws, so you can actually convert linear kinetic energy into rotational kinetic energy and back and forth, or into other types of energy. So this is just another type of energy to be included with the types of energy that we're already familiar with. We also have, with the linear case, work was force times distance, or if the force is changing, then it's integral of f dx. Well, in the rotational sense, the force is torque, and then instead of dx, we're going to have d theta, so that still works. And this was equal to our change in kinetic energy, so this is still going to equal our change in rotational kinetic energy. So this is called the work energy theorem, and all of that stuff still holds. We also defined power as the rate of change of work, w dt, so that also holds true for work done in a rotational sense. And we saw earlier that this could equal force times average velocity. In this case, it's going to equal torque times average angular velocity. So we have all of these wonderful things. Oh, also, if force is constant, if torque is constant, then you can just make this work is torque times change in your angular position, also known as theta. So let's look at an example of using conservation of energy while looking at a rotational energy situation. So here we have a rod, and it's initially horizontal, and it's fixed about this point here, so that's its axis of rotation. And if we let it go and we want to figure out how fast the end of the rod, so the velocity of the end, when it is vertical here. So we again can use conservation of energy. Initial energy is equal to final energy. In this case, our initial energy is gravitational energy, mgy. Our final energy is our rotational kinetic energy, so 1/2 I omega squared. And then we can go ahead and plug in some values for this situation. Now the y is a little bit more confusing when you have rotational situations. So the end of the rod goes from up here down to here, and the rod is length L, so the change in height of the end of the rod is L. But whenever you've got a rotating object falling like this, the gravitational energy is given by the position of the center of mass. So the center of mass only falls a distance L over 2, so that's what we're going to plug in for our change in vertical position. It's L over 2. Then we have our rod, so we need the moment of inertia of a rod rotated about the end, and that is 1/3 mr squared. And in this case, r is length L, so 1/3 ml squared. And then we've got omega squared, so we can use this and solve for omega. We can cancel out a bunch of things. The m's cancel out. One of these l's cancels out. And I guess that's about it for now. Oh, we can cancel out this half with that half. So if I solve this guy for omega, I'm going to get the square root. Let's see, the 3 multiplies up over there, and so I'm going to get 3g over L. Will give me the angular velocity at the end there. And if I want to figure out the linear velocity, then I just have to use the relation that v equals r omega. In this case, r is L, so L omega, and omega is root 3 GL. If we pull this L inside there, it becomes an L squared in here, and so we can cancel one of those, and we end up with root 3 GL, which is an interesting result because if I had just dropped this rod straight down, if it was not attached here at the pivot point, and we figured out how fast the center of mass would be going at this height here, we would just have 1/2 mv squared equal to mgl, and you'd cancel stuff out and you'd get v is equal to root 2 gl. So this is slightly larger, the end of the rod here. So we used the center when we calculated the energy, but when we converted to an actual velocity, we were finding the speed of the end of the rod. So as that rotates down through this point, it's actually going faster than it would if it had been in free fall. And here's a nice little video showing that I filmed in my classroom a few years back. So here's an old beat up tennis racket, and you'll see the end starts to fall and it moves down faster than free fall of the eraser that was sitting on top. Amazing. Some really expert footage there, I know. Alright, moving on to something a little bit different. Here, if we think about a wheel rolling, we need to be able to relate its rotational speed to its linear speed. So if you have a wheel rolling down the street or whatever, it can have both types of kinetic energy at once. It can have regular kinetic energy, or what we might call linear, or it's sometimes called translational kinetic energy, translation versus rotation. And then it also has rotational kinetic energy, so you would add those two up. But some important things: if you're watching a wheel roll by, the point that's in contact with the ground, as long as this wheel is not slipping, that point is momentarily stationary relative to the ground. And then different points along the outer edge of that wheel will have different velocities. And you can see this by this photo taken here. The top is more blurry because the top is moving faster, whereas the bottom's not blurry at all because it's actually not moving momentarily. But the key here is this velocity that the wheel is moving. If this has a given velocity and the bottom is stopped, we can reverse our frame of reference. So this is the frame of reference from an observer on the ground watching the wheel roll by. But if you take the frame of reference of the wheel, or somebody moving with the wheel, then the center would not be moving, and this velocity here, the velocity of the wheel as it rotates, has to equal this velocity here, because when you switch frames of reference, you always have to agree on the relative velocities. So if the ground says the middle is moving this fast, then the middle has to say the ground is moving just as fast. This vector looks larger here, but they are equal. This guy equals that guy right there. The guy on top is actually moving twice as fast. But this is kind of an important piece of information to have for rolling wheels or a sphere or something rolling, is that the speed that it's rolling down the road with equals the speed on the outside of the wheel from the wheel's frame of reference. Okay, now that we've got those ideas figured out, if you have something rolling down a hill, it's going to have both translational kinetic energy and rotational kinetic energy. So if you notice, when we do kinematics and even conservation of energy problems prior to studying rotation, we always have boxes sliding rather than balls sliding down a hill. And there was a reason for that, because the box does not have rotational energy, and so we didn't have to worry about it. If it does have rotational energy, that means it has less translational kinetic energy, so a sphere will actually roll down a hill slower than a box with no friction. Obviously, if there is friction, the box will be slowed down more than a sphere would be. But if we assume that this is a frictionless surface for the box will get down first. Here we have to have some friction. Don't you love how we do that? Pick and choose. Otherwise these objects wouldn't roll at all. They would just slide down just at the same rate as the box. But if we assume that these objects roll, and if this is a race and we let them all go at the same time, the sphere would get down first, and that's because it has the smallest moment of inertia. The moment of inertia of a sphere is 2/5 mr squared. Then a solid cylinder would be second. Its moment of inertia is 1/2 mr squared, which is slightly larger than 2/5. This is assuming equal masses and equal radii and all that stuff. An empty can, we don't really have a formula for that. Let's skip over that for a second. A hoop has a moment of inertia just of mr squared, so that's going to be the biggest. And we know that an empty can, if it's the same mass as the hoop, some of the mass on the ends is going to be closer to the axis of rotation than if all the mass were on the outer edge like the hoop were. So this is going to be a little bit smaller moment of inertia than this guy. But the solid cylinder has a whole bunch of mass in the middle, not just on the ends, so it's going to have a smaller moment of inertia. So anyway, that's how you can decide which one makes it down first. Now let's look at a rolling sphere a little more closely and do some analysis here now that we are considering rotation. If we want to find how fast this ball is going at the bottom of the ramp, saying that it started at the top here at height h, and we want to know the speed here at the end of the ramp, we'll do it with energy next, and that will be easier, but I'll show you the hard way first. The hard way, we can just analyze the forces acting on this, and without even considering rotation at all, we can write F equals ma equations, one for the x direction, here where we have our rotated axis, and one for the y direction. So in the x direction, we've got a component of gravity, it's going to be mg sine theta, minus friction, because that goes up the ramp, equals the mass of this sphere times a. In the y direction, basically the sum of the forces equals 0, and so the normal force is going to equal the vertical component of gravity. So we can say normal force equals mg cosine theta. Alright, then we can look at the torques acting on this sphere, and so we've got torque equals I alpha. Now there's only one force that's exerting a torque on this, because the ball is going to rotate about its center. The normal force will act up through the center, gravity will be pulling down from the center, so those aren't exerting, the lever arms are 0, those aren't exerting any torque. So the only torque we have is friction, so we're going to have friction times the distance, which is the radius of the sphere. I, as I mentioned earlier, is the moment of inertia of a sphere, which is 2/5 mr squared. And then alpha we can write as a over r, so that cancels one of the r's, that other r goes away, and we get that friction is equal to 2/5 times the mass of our sphere. Now if I go back and plug this in up into this guy, I'll just rewrite it over here, so I've got mg sine theta minus 2/5 m equals ma. Wait, I lost my a. I was like, hold on. Okay, so my a is still over here, which is good, because then I can combine these two terms. I can add 2/5 over here, so I get mg sine theta. So this is 1 plus 2/5, so 5/5 plus 2/5 is 7/5 ma. I can get rid of my masses, and then if I solve this for acceleration, I'm going to get 5/7 g sine theta. Now that wasn't the final question we were asking, but this is a useful bit of information. This is true for all spheres rolling down ramps if there's friction. You might remember a box sliding down a frictionless ramp, the acceleration is g sine theta, so the fact that it now needs to rotate will slow it down a little bit. And now we can do a kinematic equation to find the velocity at the end of the ramp. We can just use v squared equals v naught squared plus 2a delta x, because we have a constant acceleration, even though we have this other factor in there. It's still constant, so we can use our traditional kinematic equations. We're going to assume that it was released from rest. So we have the velocity at the bottom of the ramp is square root of 2a delta x, and then we can plug in the information we know. The acceleration we just found is 5/7 g sine theta. Now delta x, if we think about this ramp here, there's our theta, this is the opposite side, and delta x is the hypotenuse, so it works out that delta x is h over sine theta, which is nice because these sine thetas will cancel out, and then we just have the square root of 10/7 here times g times h, which once again is slower than it would be going if it just rolled down. Then this would be root 2gh would be the speed of a box rolling down a frictionless ramp. So this is a bit less than 2, so it's not going quite as fast. We can do this same calculation, finding the speed at the bottom of the ramp of a ball rolling down here with conservation of energy, and it works out a bit easier that way actually. So we've got our initial energy and our final energy being equal to each other. On this end, we've got gravitational energy. Our final energy is our regular kinetic energy plus our rotational kinetic energy. So we can start plugging things in here. This is going to be mgh. Linear kinetic energy is 1/2 mv squared. Rotational kinetic energy 1/2 I omega squared. This guy here, I was going to be 2/5 mr squared, and then omega squared, we can write that as v squared over r squared. So r's go away. We still have these terms here. mgh. Masses can cancel out. And so what are we left with? Well, we've got a gh here. We've got 1/2 v squared and 1/2 times 2/5 v squared. So that's going to be v squared times 1/2 plus 1/2 times 2/5. And that goes away, so we have 1/2 plus 1/5. So that is, what, 5/10 plus 2/10, so that's 7/10. Ugly 7. 7/10 v squared equals gh, and that works out to be the square root of 10/7, which is what we had before. Probably a little bit easier this way, doing it with energy. Now, there are some problems where you have to combine conservation of angular momentum and conservation of energy, like we did with our inelastic collisions. And so let's look at an example of doing that. These can get a little hairy. If we have a rod that is hanging from some pivot point about its end, and if we have a chunk of clay, let's say, that gets fired and splats and sticks on this rod and sends it going up this way, and we want to know how high the end of that rod ends up going. So the rod will end up something like that, and we want to find this distance h here. Given some information, let's say the mass of this piece of putty is 1/4 kilogram. Let's say the mass of the rod is 1 kilogram. The length of the rod is 30 centimeters. I guess I'll cram that in there. And let's say the initial velocity of this ball is 10 meters per second. So you might attempt to use conservation of energy to do this and find the kinetic energy here and just set it equal to gravitational energy and ignore the fact that this was rotating at all. The problem with that is the same problem we had before, where you dissipate some energy. You're creating thermal energy in the collision, and we don't know how much, so we can't do that. But we can do conservation of momentum for the collision, but because it's fixed here, we can't do linear momentum. We need to do conservation of angular momentum. And so we can say that the initial angular momentum equals the final angular momentum, where this is right before the collision and right after the collision, before it is started swinging up. So before the collision, again, we have this point particle, and we're going to consider it as having angular momentum with respect to this point here. And if you remember, you're going to take rmv to find the angular momentum of a particle relative to a specific point, where r is the closest approach to that point. So in this case, I won't plug in numbers quite yet. Alright, then we need the final momentum, so that's going to be I omega. I is going to be the I of the rod, which is 1/3. I'll use a big M for the rod and a big R. So, and that's supposed to be 1/3. So go away half. 1/3 M R squared. Plus, we can treat this as a point particle, so that's just going to be little m, little r squared. And that is the total moment of inertia, and then that times the omega, because this is I omega, right? So now we can go ahead and plug in some numbers. We've got 0.15 is the closest approach here because it's hitting in the center of this rod of length 30 centimeters. The mass of the clay we said was 0.25 and its velocity was 10. We can set that equal to 1/3. The mass of the rod was 1 kilogram. R is the length of the rod in this case, so we need 0.3 squared plus the mass of the clay times its distance from the axis of rotation, so that again is 0.15 squared, and we can solve this guy for omega. By the way, this term here, the total moment of inertia, works out to be 0.035625. We're going to use that later, so that's why I'm writing that out. So if we divide that over and solve for omega, we get an omega of 10.526 radians per second. So that is omega right after the collision, before it has started to swing up. It slows down as it swings up, obviously, and from this point we can use conservation of energy, and we will set our initial energy equal to our final energy. The initial energy is the rotational kinetic energy, so 1/2 I omega squared, and the final energy is going to be mgy. And so this is the same moment of inertia that we found here, so that's the nice 35625 thing. And then omega we've got here, so 10.526, that gets squared. This mass here is the total mass, so that is going to be 1.25 times 9.8 times the height. And so we go ahead and solve this equation, and we get a height of 0.16 meters. And this is the height of the center of mass. That's this point here. And if the rod is, well, the end of the rod, it's going to be twice as far, so we could just double all these distances because they will be similar triangles. So the height of the end of the rod is just going to be 2 times 0.16, or 0.32 meters. So there you go. Lots of fun. One last little thing I wanted to talk about, now that we understand a bit more about rotation, is the mystery of why a rolling ball will stop. Because if you think about the forces acting on a rolling ball, you've got a normal force going down, and that is just going through the axis of rotation, so that's not exerting a torque on the ball. Sorry, normal force is up. Normal force going up, gravity going down. But those are both acting through the center, and so those won't cause torques. Friction, you would typically think, is slowing down the ball, but friction is acting in the direction of the rotation, so that would tend to speed up the rotation. So why in the world does a rolling ball ever stop? Well, what happens is that there's no such thing as a perfectly solid object. So on the microscopic level, the ball will deform a little bit, the surface will deform a little bit, so that normal force isn't just acting. If you had a perfectly rigid object on a perfectly rigid surface, that normal force would act only on that single point of contact. But here you have a whole bunch of points of contact, and so you essentially get normal forces over here, which is off center of the ball, so that exerts a torque in the opposite direction that the ball is rolling, and so that's actually what slows down and stops the ball. So it's not all that correct to say that friction stops a rolling ball. They do refer to this as rolling friction, but it definitely behaves differently than than the regular sliding friction. You wouldn't use mu times the normal force to analyze why a rolling ball stops. Okay, that is all. Have a good one. See you next time.